Okay, so now recording is started. Again, thank you very much for reminding this. And my name is Aditya Rawal, and I'm one of the TA for this courses. And today we will talk about the encryption. So let's see. You guys can see the slides.
Yes.
All right, thank you. Let me just close this. Okay. Okay, so this is one of the quotes by one of the authors. They are saying like there are two types of encryptions. Like one will prevent your sister from reading your diary, and one that will prevent your government, right? So it's the level of security, how much secure you want to make the stuff. Like there are simple encryption and there are like harder encryptions based on the money and resources you will spend. Like you will get that much security. And today we will talk about the encryption. Let me just see. Okay. So there are like security tools. So encryption is one of the security tool, but it is useful, but it does not solve all the security problems, right? And it can assist in maintaining the confidentiality and integrity of data. It can make sure like your data stays secure as well as some unauthorized person does not change it. And generally we have the cryptography. So cryptography in that particular thing, you have your source material. Can everyone see my pointer? The mouse pointer?
Yes.
All right. So usually we have a plain text and we want to encrypt that particular plain text. So plain text can be anything, like it can be graphics, it can be text, it can be streaming data, it can be some kind of bits, it can be anything. So that is your original source material. And you perform an encryption that is like a process of deciphering that data and making it unreadable. And after as the output, we get this ciphertext, right? So usually we have some kind of key that we use to encrypt our data, and the same key, or in some cases like a different key, can be used to decrypt that data to achieve the plain text again. At any point, if you guys have any questions, you can just stop me right there and just ask the question. So the ciphertext is the encrypted form of the plain text. It looks like a random collection of bits. It can be like simply a scrambled message, or it can be some complicated symbols. It can be some kind of, let's say, weird rearrangement of the letters. It can be anything. And it usually associated with some kind of key. And there are processes like compression and encoding, such as like base 64 encoding, right? Now, a little bit of history about this. People have been using this for like a very long time, millennia, right? The first person was, I think, the Caesar. He was the Roman general, this person. And it was used by the Julius Caesar. So, and most important thing about encryption is like computationally, whenever you do the encryption, it should be efficient, right? Now, encryption can be of like two types. One is like encryption when data is in motion. So most of you must be familiar with VPN, where you guys establish a secure channel and like your all the data that you communicate over the internet, that is encrypted, right? And another type of encryption is when data is at the rest. So that can be, if like, I'm not sure about the Mac, but if you are on the Windows, it can be BitLocker or some other type of technology that actually encrypts your all of your data that is stored on your hard drive, right? And first thing that we have is like Caesar cipher. This is the simplest form of cipher. where we have some letters from the A to Z, like total 26 alphabets. And we use that particular letters and we shift the numbers to do the encryption. And mostly in this case, the key is the number of times you shift the letters. So it can be 2. So if the key is 2, then you just shift the letter by 1. Like you can, let's say you have A to Z, then your shifted letter will start from B to A. So that will be your key 1. That way, whatever the number is defined as key, we just shift that much, right? Now, if we have if we have this ciphertext, and if we want to decipher it, computers can easily do these things, right? Computers can easily decipher this particular ciphertext and get the original content. So let's say you shift by 1 letter. In this particular ciphertext, your key starts from, let's say, F. So you go from F to E. But when you shift by 1, like during the decryption, you have to shift backwards. But when you encrypt, you shift forward, right? So when you shift 1 time back, then you get E to, I think E to F ends at F. And that way you just get this kind of decipher, right? This is one attempt by computer to decipher this particular thing. Then computer again tries it a second time, right? By doing 2 shifts. And at the 3rd shift, it actually gets what was the original content, right? Computers are fun. That was the original content. Anyone have any kind of questions on this? The Caesar cipher brute force thing? I think no, because no one is saying anything. Okay.
Can you explain again, please?
Okay. Okay.
Thank you.
All right. So let's say we have a ciphertext, right? That goes from, let me see if I can do something else here. Can you look at the chat, right? If we have a ciphertext that goes this way, right? If we have original text that goes A, B, C, D, right? Then you have your ciphertext that is like, that starts from E. So the first attempt is that starts from E, that goes E, F, dot, till D, right?
Mm-hmm.
So this is your shift by 1. So you are actually shifting all the letters by 1 only. So that way this cipher actually works. But what computer is doing is it's trying brute force. Brute force is trying all the combinations, right?
Mm-hmm.
So this way, if you need to decipher this, you just need to do it 26 times, right? Computer can shift by 1, and then in 26 attempts, it can find your original text. Does that make sense?
Okay, not completely, but it's okay.
Okay. So let's say let's go opposite way. If you want to encrypt this, right? Computers are fun, right? And your key is 3, right? So you shift the letters by 3. Now when you do the shift letter by 3, at that time your C becomes F, right? And that way, like whatever you have written as your ciphertext, you just like compare the letters, and then you get the output for the ciphertext. Does that make sense?
Okay.
All right. Okay, sounds good. Let me just go back again. Okay, so normally we have like three types of, or maybe 4 types of attacks, where you have like where adversary can try different ways. to get the answer for the encrypted text. So first one is like ciphertext only attack, where the attacker has some kind of samples of ciphertext. It can be any situation where he is trying to break into a system. He does not need to know the password or something like that exactly, but he knows the exact cipher. Then he can just like put that information inside the system and get access to it. So that is your ciphertext only attack. Now another one is known plain text attack. In this, the attacker has like corresponding pairs of plain text and ciphertext. So based on some type of key, he already has a plain text and he knows what is the exact ciphertext for this. And he uses those examples to do the attack on your system, right? Another thing is like chosen plain text attack. In that particular thing, he specifically chooses some plain text, and he also knows what are the ciphertexts for those particular examples. In that particular case, his goal is to guess the key. What is the key that actually matches the particular stuff? Any questions on these three types of attacks? I think no. So let's talk about the first one, that is substitution cipher. So in this particular cipher, the letters are actually mapped to symbols or some other letters, right? This key, the key is an alphabetical list of symbols, right? Here we can see like each symbol is mapped to some alphabet, right? And based on this, if you have like 26 26 alphabets, then there are 26 factorial possibilities, like possible keys. And if computer does the brute force attack, it just needs to do all check for all the 26 factorial possible keys in order to find the right answer, right? Now, usually in this type of cipher, this type of material is already available online. The frequency table, which is used, this uses the letters of frequency in the English language. So we all know like most of the English sentences have this alphabets in a higher order. Like let's say in all the words we have more E's, more T's, more A, and all those particular letters, right? So there is a very high probability if you just find the maximum number of symbols or maximum number of letters and you replace them with E, T, and A. So you just do it in ascending order. Like first you replace the maximum number with E, the next thing is T, and then A. So particularly if you go that route, most of the time you will get some kind of answer, right? So here we have a ciphertext that is actually encrypted using the symbols, right? So can anyone know like what this is trying to say? I know this is some similar sentence told by Chancellor Martin, but like, can anyone guess like how we will solve this particular thing?
You could look at the most common symbol and start with that. It might be an E, and then the next most common might be like an A or a T.
Right, you are absolutely right. That is exactly the case. Now, if you just try to substitute the things, right? If let's say if we just go over this particular text, then this M symbol repeats maximum time, right? And you don't have to know this. Most of the time your computer will calculate this. Like what is the maximum number of symbol that occurs in this particular thing? Your computer can easily tell you which is the highest number of symbol, right? So you just replace that with E. So in this particular case, right, if we just think about this example, then as you can see, the M is the most common. This M symbol is the most common thing, right? So we replace that particular thing with E. The next most common thing is diamond, right? Now, this is already given, but like your computer can easily tell what is the maximum number of symbols in this, right? So the next one is the diamond. So you replace it with the second most frequent word, letter. So that is T, right? So you replace the diamond with T. And that way you just go with the frequency table. And when you try, then you get like some kind of message that makes sense. Now, again, this is not exactly perfect, right? This message. But as a humans, we can actually understand like what this might be, right? So the original text for this particular thing was, "Welcome to North Carolina Agriculture and Technological State University." But this is something that we can make sense of it. But we were able to decipher it very easily using just one tool, that is the letter frequencies, right? This particular chart, if we just use it, we can solve this particular thing. So let me see if we have those things here. The poll. So how do you do that poll thing? Does anyone know? Okay, let me see. Okay, so we don't have polls and we don't need to do that, I think so. So let's just go here, right? So this is the question. Like, anyway, everyone can see the question, right? So a cipher is, then you have like this options, and is a like, this is a type of mapping, but what type of mapping it is between plain text and the ciphertext? Can any one person or like someone just try to guess this? Oh, I think someone just guessed it.
One-to-one?
Yes, you are exactly right, sir. So it's one-to-one mapping between the plain text and ciphertext. Now you were thinking like, why is it one-to-one mapping, right? Because each and every letter, like if you just go, this L is mapped to this particular symbol, right? This M is mapped to this particular symbol, right? So that way, if you just go, then it's one-to-one mapping between all the words. Now, many symbols will repeat, but still it's one-to-one mapping, right? One symbol relates to other letter. Okay. So now we have another cipher that is called Visionaire Cipher. And originally this was described by Giovan Battista Belasso in 1553. And the key for this cipher is like it uses mathematical properties to do the encryption and decryption, right? So to do the encryption, it actually creates the ciphertext using the pair of plain text plus key and then doing mode 26 to that particular number, right? And in the opposite way, when you want to decrypt this, in order to get the plain text, you need to do ciphertext minus, so that is like subtraction of the key, and then you do mode 26 to get the decipher, right? So here, like we have one of the example, right? We have our example, "Welcome to North Carolina," right? Now this is our plain text and our key is information privacy. Now, one thing, whenever we have like the original plain text length is greater than the key, we just repeat the key over and over again, right? So in this case, the information privacy covers still RO. Still we have lina left, LINA, right? So we just repeat the key and we say info again, right? Now, can anyone guess like how this thing is working? How this ciphertext is created using this plain text and key? Anyone? Oh, I just stopped it. Anyone?
Is it the position of, so start with the first letter, the position of the letter W plus the position of the letter I will give you E?
Right. So that's the basic thing, the position of it. So mostly in, let me just see if I can get out of this. Okay. So this is some basic resource, right? Where each of the letter is marked with the index of that particular letter, like particular letter, right? So A starts from 0. We have 26 alphabets. So like that's from 0 to 25, right? All of them are mapped. You can find this kind of things by just doing a simple Google search, right? So each letter is mapped to its index, right? So if we just go here and we see, first one is like we have welcome, right? So that's W. So W, the position for W is 22, right? Then we have our key, and I is our key letter, the first letter of our key. So that is 8, right? So if we just use this formula, then first one is like W. So we have 22, right? Everybody can see the calculator, right?
Yes.
Can I? Yeah, okay.
Yes.
Thank you. Okay, so W is 22, right? That's the position of W. And we have our key, the I, right? So I is at 8, right? So we just do 22 plus 8, and then we do mode 26, right? So that gives us the 4. So corresponding ciphertext should be the letter at the 4th index. So that's gonna be E, right? So this way we actually use this mathematical properties to encrypt the whole thing. This way we create plain text from ciphertext. Now, if we want to decrypt it, can anyone tell me like what will happen if we want to decrypt this stuff? Anyone?
So we subtract the positions from the letters of cipher and key, like position of E should be 4
Mm-hmm.
and the key should be it's 8. So I mean we can take the magnitude of that, avoid the symbols because it's a mod, and I mean it will come on.
So usually what will happen is like when you encrypt, if it's the same key, then you do the reverse process, then you will get the reverse way, right? When you encrypt, you do the addition, but you decrypt, you do the subtraction, right? So right now you're looking at the ciphertext. So your ciphertext letter is E, so that is 4, right? Again, like if you have 4, then you do the subtraction, and then you just do it from the key, right? So your key is 8, right? Because the first letter is I, and that is 8. So that will be -4. And if you do -4 mode 26, then you will get 22. So our plain text should be the letter whichever comes at 22 index. So that is W, right? So it's exactly opposite of how you encrypt this. Now, all these processes, computer can do these processes very quickly, right? Because it's very fast. But there is still another way to do this Visionaire cipher, right? There is another trick. It is called Visionaire Square, right? So everyone can see this square, right? Visionaire Square.
Yes.
Yeah, we can see it.
Right. So at the top, we have the plain text, right? So this letters from A to Z, like those are the plain text, your plain text, right? This A to Z is your keywords. And everything in the middle, that is your ciphertext, right? So let's try to do this example. If we see W, right? So our plain text is W and our keys letter is I. And if we need ciphertext for it, then we just look at the W here, right? This is W and this is I for your key. So the corresponding letter for your thing should be E, right? Because in ith row and W column, you can see this is E. Can everyone see this hand, a little hand that I have? Right? So that way we can actually use this square to actually see how the encryption and decryption works for this Visionaire Square, right? So does anyone have like any kind of questions about this cipher, particularly in any of the method, like the mathematical or the square method?
Would you be able to explain one more time what exactly, I guess, the mathematical logic is to decipher the text? Or I
Okay,
guess encrypt or decrypt?
right. So the thing is, let's say when you want to create if you want to encrypt something, right? If you are encrypting, you actually need a plain text and a key to produce a ciphertext, where decryption is the opposite process, where you have some ciphertext, you know the key, and you want to obtain the plain text, right? So this is the mathematical formula where you need to obtain the ciphertext of I. So let's say if we are doing it for the first letter, W, right? So that is at 0 index. So if we can just see cipher of 0 is equal to P of I, plain text of I. So that will be again 1, right? So in your plain text, it's W. So here you can see W, but you need the count of index of that particular letter, right? So W is at the 22 position, right? See here, W is 20. This is nothing, like it's just A is mapped to 0, B is mapped to 1, C is mapped to 2. That way we just map all 26 alphabets here, right? This is just the mapping. So what we are doing is, like when we want to encrypt the text, we are just saying like our plain text is at 22 index, that is W, right? Then we add that particular thing with the key. So our key is information privacy, right? So the first letter is I. So the position of I is 8, right? So you just do 22 plus 8. And then you have to do mode, right? The mode is the mathematical thing, right? If you do mode 26, then you will get some kind of position. Oh, I think I didn't do this. 22 plus 8. Yes. And then mode. And then you do 26. Then you will get an answer. That should be your corresponding ciphertext, right? So which letter comes at the position 4? So that is E, right? So that way you just encrypt this to E. Does this explain?
Yes, it does. Thank you very much.
All right, no problem. And anyone have any questions about the square, the Visionaire Square? Like it's not here, but it was one of the easiest thing that I found. If we want to do it manually, then that's easiest way to do this. So does anyone have a question about that, the square? I guess not, maybe no. Okay, then let's go ahead. Okay, so Visionaire cryptanalysis, like it's now for long text and short keys, right? The character frequency analysis can work great. Like we have seen that particular, this long paragraph. For this, like our frequency table works best to decipher that information, right? And sometimes the same plain text letter can be used to encrypt by the same key characters, right? So let's say if you have some type of chosen plain text and ciphertext, and you also know the key, right? At that time, if you find some meaningful words, you can actually see the portion of that particular letter and you can see, okay, so this cipher corresponds to this kind of plain text. And if you just try to map all those things, then sometimes in a big thing, you will just find like couple of words. Those are repeating. And somehow you will be able to reconstruct that. So it's all about like trying different combinations. But our advantage is like we are using computers and they are like extremely fast. So this guessing process might take us a long time, but for computer, it does not take a long time. It happens very quickly, right? So statistical analysis on the frequency and distance, right? That's the same thing. Now, the another one is like running key cipher, right? This one is also called the book cipher. And this cipher is very similar to Visionaire cipher, but it has a very long key. And none of the key letters repeat, like there is nothing like it. In the first one we have seen, we were repeating the key. Once the key is done, we are going to repeat the same key for the rest of the letters, right? But in this one, our key is like very long and sometimes has the same length as your plain text, right? And in this case, typically people use common publication books and common articles or some kind of stuff where people need to say, okay, on the page 1 of this book, just try to compare it with the ciphertext and you will be able to decipher it, right? And the well-known example here Dr. Williams gave is from C book, right? So the plain text says, fleet at once, we are discovered, right? This is our plain text message. And the running key is taken from this C book. So this book is saying errors can occur in several and then PL, maybe something else. So that's PL, but this is the length of our plain text. So we are just taking this much key, this much running key, right? And then we generate the ciphertext. So does anyone want to take a guess like how this ciphertext is generated here? This F to J. Anyone?
Is it doing something similar to the Visionaire cipher?
Yes, exactly. It's very similar. So it's a very simple 4-step process, right? They are using here. Can everyone see these notes that I have written here, right? On the comment box?
Yes.
Right. So first of all, they are taking the plain text and converting it into an integer, the same thing that we were doing earlier, right? So here we have F and our special mapping that we were using earlier, right? So F maps to 5, right? 5 index. So we have our F as a 5. Then the next thing is you just get the key and convert that letter to integer. So we have E and the index for E is 4, right? Then we add the plain text and key letters. So that is like 5 plus 4, that is going to be 9. So we just like get the index of both and then add it, right? Now note, if our sum is greater than 26, greater than or equal to 26, then you need to minus the 26. Let's say if you go over 26, right? Some letters, if you have Z and something else, let's say Z and F, then you have 25 plus something, then you will go more than 26. Like that number is going to be greater than 26. At that time, at that time, you subtract 26 out of it, and whatever you get, you just convert that particular thing back to a letter, right? So here in this example, we have 5 plus 4, that is 9, right? And 9 is corresponding letter for J, right? So this is how this running key cipher works. Now, can anyone tell me like what is the advantage of using this running key cipher? Like what is the best part of using this instead of Visionaire?
It like adds another step.
Yeah, you are partially right. It adds another step, but the thing is your key is never repeating. You see, your key is constantly running. You are not repeating this, and it's much harder to guess some kind of word and do the chosen plain text and ciphertext attack, right? On this particular thing.
Yeah, yeah.
Right. And this is also called one-time pad. So your this running key, which is like very unique, it is also called one-time pad, right? Now in this one-time pad encryption, the bit stream of the message is XORed with the random key. So mostly your key should be random for this thing, and XOR is the operation. So anyone here does not know what is the XOR operation?
What is that?
Okay. So XOR is a type of a gate. So in computer, everything happens in 0 and 1, right? So XOR is basically a gate where you have two inputs. And if you have XOR operation, then you get exclusive OR of that particular thing. So let's say if you have your inputs as 0, 0, so your A is 0, B is 0, then XOR of that particular thing is 0, right? And similar way, if you have like 0, 1, 1, 0, and 1, 1, this inputs. Now the easiest way to remember XOR operation is to, when two inputs are same, the result is 0. And if two inputs are different, then result is 1. That's the easiest way to remember this XOR, right? So in this particular one-time pad, they actually use the properties of XOR gate, right? Where your first input is the plain text and your second input is going to be a random key. So as it says, the key must be as long as the message, right? Because you are not allowed to repeat the key. And the key must be truly random, not just something pseudo-random. And most of the time as a human, we will pick some type of key that repeats somehow. It's never gonna be like truly random. There is a way you can use a random generator, right? It will definitely generate something random for you. So your one-time pad is a perfect encryption technique that cannot be broken. Because if you are not repeating the key, then there is no way that someone will predict, okay, so this type of pattern is occurring in the encryption, or this kind of repeating words are coming in, because it's truly random. So it's perfect encryption, right? So now my question is for you guys. So why don't we use this everywhere, right? If it's the perfect encryption, why don't we use it everywhere? Anyone? Okay, so I'm not sure if Dr.
Oh, is it something where it cannot go both ways with? Oh, actually, sorry, never mind.
No, it's fine. So whoever talks, like it's good that you tried actually. The thing is, I think Dr. Williams must have talked like security is kind of a trade-off between time and the value of the information, right? So let's say if your information is valuable for limited time and after that it's useless, right? You don't want to spend too much effort on doing the encryption. So as long as the information value is less than the time to encrypt, right? So if, let's say, if you have some information that is valid for only 10 minutes, and for that particular thing, if you encrypt that data, it takes you 1 hour, then that is not a good scheme, right? Because let's say after 1 hour, if someone decrypts it, it's useless. So in that particular scenario, your system is secure. So we always try to look for that kind of trade-off in the security world. Okay, so it was a little bit off topic, so let's just get back to here. So now in this particular example, a ciphertext is given, and they are trying to do the decryption using a key, right? So everyone can see here we have the ciphertext, right? 011 001010, right? And we are using this key 0011 00000. So now we do the XOR operation. Now remember, when I say if the inputs are same, it's 0. If inputs are different, it's gonna be 1. So first thing is like 0 0, so it's gonna be 0. Then we have 1 0, that's gonna be 1 because they are different, right? So that way we are able to decrypt the whole thing with the help of a key. Now, this is the running key analysis of our running key or one-time pad, right?
Hi, hello, excuse me.
Yep, go ahead.
I have a question.
Yeah, go ahead.
For the running key
Hmm.
cipher,
Hmm.
I was thinking, how do you decrypt it?
Okay. So if you want to decrypt this, right, it's gonna be the similar process that we did earlier, right? You do the exact opposite of what you did earlier.
So if the sum is greater than 26, you add.
You are
or
going
you
to add, right? You are going to add here, right?
okay.
So if you're in this case, what will happen if you try to decrypt it? Your first value is going to be smaller, your second value is going to be larger. So you will get something in negative, right? So you will get something like -4, -5. Then you
Yeah.
just add 26 into it, so it becomes
Okay.
positive.
Oh, that
And
makes
then
sense.
whatever letter is there, you just map it to your plain text, right?
Awesome.
And that way you
Awesome.
just get the output.
Okay, thank you.
Yep. Thank you for asking that. I actually forgot to mention that thing. Okay. Anyone else have any more questions about this? I think not. Okay. Okay. So here we were talking about the human tax is relatively poor, right? It's very hard to pick something extremely random by humans. And if you know some part of plain text, you can actually abstract it, as I said earlier, right? If you know a particular word in the string, then you just have to extract those passages, like those words, and you can actually arrange them and make some kind of educated guess what that particular thing is going to be. Again, as humans, it's going to take too much time, but for computer, it's very easy to do because it can do so many attempts in so little time, right? To guess something and make sense out of it. Now, another thing that we have is like diffusion and confusion, right? So these are the properties of encryption. So diffusion is spread of the plain text over the ciphertext, right? And it's also a byte of plain text should impact many bytes of ciphertext. So does anyone know what this particular sentence, a byte of plain text should impact many bytes of ciphertext? Can anyone guess like what kind of property is it in the computers? So this is one of the important properties of computer science, and it is called like Avalanche Effect. right? Where you just make a small change in your plain text and it will have like a very big impact on your ciphertext. So if you make a smaller change, then your ciphertext will change too much. And this is one of the biggest properties of all the encryptions, right? So with DES and AES, if you change one bit of the plain text, it will change more than half of the ciphertext, right? And this is a desirable property in the encryption that we want. And the second one is like creating some kind of confusion. So mostly those are the changes on the plain text based on some type of rule that we define between two people. Or maybe it can be some mathematical concept where we define some rule to change it mathematically to something else, right? So now there are two types of encryptions. One is symmetric key encryption, or it's also called secret key encryption, right? And another one is asymmetric key or public key encryption, right? Now, in symmetric key, the encryption and decryption key are the same, right? And there should be some other way for the sender and receiver to securely exchange the key. So it's going to be the same key that is going to be used for encryption as well as decryption. Now in asymmetric key system, each user has two different set of keys, right? So as a user one, I have encryption key and I have a decryption key as well. So that is the basic difference. And in this system, you don't need to share the keys. You don't need to secretly share your keys, right? And the encryption your encryption key or your public key can be made available while you just keep your decryption or your secret key as a private to yourself, right? So here is a simple diagram, right, for a symmetric key cryptography, right? So your AES and DES are example of this encryption, right? And the basic point is your key to encrypt the message and decrypt the message is going to be same. And you need some other way to send your key securely to second user, right? If you are encrypting. So here we have plain text, right? And we have some secret key we use to encrypt our message, and then we create a ciphertext out of it. Then we send that message to user 2 over the internet, and user 2 uses the same key to decrypt that plain text. And this system is called symmetric key system or private key system, right? Does anyone have any questions for symmetric key? Guess no. Okay. And the next one we have is asymmetric key cryptography, right? So this is also called public key system, right? Where each user has two different keys. So one is your encryption key, that is your public key. And second one is your private key, that is your decryption key. And in this case, you make your encryption key available online in public key directories, right? So let's say if I want to send a message to user 2, then what will happen in this case? Can anyone tell me? If I like in this system, what will happen? You can just guess. You don't have to be correct for this.
It'll get the public key from the directory.
Right. Right. Absolutely right. So you just, let's say if I'm user 1 and I have to send a message to user 2, then I just look up the public key directory and get user 2's encryption key or public key, right? And I use that to encrypt my plain text and send it as a ciphertext. Now, the basic advantage is that nobody can decrypt this. only user 2 can decrypt this because he has the decryption key for that particular encryption key, right? So when user 2 receives it, he just needs to use his decryption key or his private key to decrypt this text, and he can read what was sent in the plain text, right? So RSA is the encryption example of asymmetric key cryptography, right? I know this RSA corresponds to 3 scientists, and first one was Rivest, other two I forget. So if anyone is interested in looking up, you can just, I think it was Rivest, Schmidt, and A was Edelman. Yeah, I think Edelman. Yeah. Okay, so any questions on asymmetric key cryptography? I think no. Okay. So why public key is a standard, right? So we these are the standards, right? DES is data encryption standard, AES is advanced encryption standard, and these are the algorithms, right? Those are published online. So why not we keep this algorithm secret, right? Now, to be useful, somehow others needs to implement this particular algorithm, right? And a good algorithm is it like any algorithm, when can you know it is good or bad? Can anyone guess? Okay,
It's
So-
good if it's fast and efficient.
right. Yeah, it should be fast and efficient, but one of the basic thing in this particular thing is, like, if you publish the algorithm, there should be no way that you can break it by just knowing the algorithm. But if you know the key, you can decipher it. That makes a good algorithm inside the security domain, right? So in order to make sure everyone can use this, you need to publish your algorithm, but it should have some kind of mathematical properties that will make sure that having the knowledge of algorithm does not give you the power to break it. You need key in order to see the plain text. So in security, that is actually called the good algorithm, right? So this is just the basic of encryption, right? So RSA is the asymmetric key encryption, and it is slower than DES and AES. DES and AES are very easy to implement on the hardware because they use the same key. There is no need for public directory, right? And it's very efficient. If you have a single key, you can do basic mathematical operation and it will give you the encryption and decryption, right? And AES can be efficiently implemented in softwares as well, right? And any type of hybrid system that uses like a combination of both type of systems, right? It is called hybrid encryption. And in most of the times you will see many secure system will always opt for some type of hybrid system where the first correspondence they will try to use asymmetric key because it's more secure, and then they will try to convert it into a symmetric key type of system because it's very fast. You need to use only one key to do both, right? Okay, so any questions on this till this point? I think not. Okay. So basically the key strength, right? So the longer is your key, harder it is to brute force that attack. Now, can anyone tell me why this is the case? The longer is your key, it's harder to break.
I think it's so because at some point so since this is gonna be running on a computer, for example, if the key is longer and a brute force approach is used, then the brute force approach keeps trying out several things until it gets to a certain point where the computer has to maybe retrieve resources, retrieve memory, so it can assign those memory to other applications that need it. So at some point, the brute force use or system might get terminated in the process because it has exceeded the amount of memory assigned to it to run.
Yes, you're exactly right. So let's say if you have a key that is like n bit, right? And it requires you like to guess all the combinations. You need 2 raised to n guesses, right? That is like exponential. So if say like the biggest property or the strength of the key is that like if you have n bits, like if you change from 3 to 2 or like 3 to 4, then you are changing your number of guesses exponentially, right? So that way it's going to take much longer time for a computer to figure out what type of or guess the exactly what is your plain text, right? And it is said that like if you have 2 raised to n guesses, then you are most likely to correctly guess the answer in 2 raised to n minus 1 try, right? So let's say if you have a simple 3-bit key, right? That is like just 3 letters, right? Then you just need 2 raised to 3 guesses to try all possible combinations, right? So those are only 8 guesses, right? And you are likely to get in 50 percentage of the time, you are likely to get the correct answer in 4 tries, right? And asymmetric key algorithms, they require mathematical relationship between the key and not every bit of the string. So that's why they are more secure, right? Because the mathematical relationship is between your encryption key and your decryption key, right? This will be explained by Dr. Williams in next class because he is going to explain DES, AES, RSA, all those algorithms, right? But the simple thing is like the key lengths. So DES uses 56-bit of key. Triple DES and DES3 uses 112 bits of key. AES uses 128, 192, or 256-bit keys. And RSA uses the 512, 1024, and 2K bits in the length for the key. So based on this, what do you think? Which one is the most secure?
The 256-bit.
RSA.
Right. RSA is the most secure thing. But why don't we use RSA everywhere? Can anyone tell me that? Like if it's super secure, then why we use AES?
I think because in the previous 2 slides you mentioned it's slower than AES and DES.
Right. It's very slow and it's computationally very expensive as well, right? So in RSA, you have to look up a key in public directory, then you encrypt your text and then you send it, right? So we are using 2 different keys in this case. But in the case of AES, we are just using a simple 1 key, right? And right now, AES 256-bit is like very much secure, but most of you know now quantum computers are coming in the picture, right? And it can do much more damage very quickly. So this was one of the additional thing. And okay, so any question? I think we will stop here today. We will not go over much more content, but anyone has any question before this? Let me just do this and yes. Does anyone have any questions?
So the longer the encryption key,
Hmm.
the harder it is to crack the encryption. Thus, the more secure the algorithm or the encryption.
Right. You're absolutely right. So the longer it is, and the thing is not repetitive key, right? So if you are able to find some kind of pattern inside the text, then it's much more likely that you are able to guess what is the correct way. So if we see the perfect encryption, that is the one-time pair, right? Where your key is extremely unique, it does not repeat, it does not create any kind of pattern, but we don't use it because it takes too much time, right?
Right.
And
And the hacker
length,
just gives up and they want something easy.
right? And sometimes it's possible your information value, the value of your information is not important after some amount of time, right? So
Right.
as long as you are able to encrypt something in that time frame, and if it takes attacker to break that encryption more time than the value of that particular information, then our system is secure at that point, right?
Right. Right.
Right.
Right.
All right,
Yep.
then. Anyone else have any other questions?
Yeah, I have a question. It's not
Mhm.
related to today's class. Just
Okay. No problem. Go ahead.
I noticed the slide you're presenting or you presented.
Mhm.
It's not available on Blackboard.
Right.
When is it going
So
to be available?
this recording and slides, they both of them will be uploaded by Dr. Williams, probably by tonight or
Okay.
maybe tomorrow morning,
All right, got you.
because
Thank you.
he's traveling, right? So
I see. That makes sense.
right.
Thank you.
And he will continue this slides because there is still some content left. So he will continue this slides again on next lecture, Wednesday.
Gotcha.
All right. I think so. We will end this session here a little bit early, but if you have any questions, just let me know. Okay.
Thank you.
All right.
Thank
Thank you very
you.
much.
Yes, thank you.
Thank
Yep.
you.